Okay, can you see it, my screen?
Yes.
Yes.
Okay, this paper is a low cost and accessible method for a rapid fabrication for the modificable microfluidic devices. Uh, I think that is just the that I that we need. In this paper, they prove with a new polymer. In this case, is an EVA-based microfluidic type. What is the EVA? Is ethylene vinyl acetate. Is that is as a very expensive polymer, and they can use it just with heat. And they have it have several advantage in comparison with the PDMS. The fabrication, the first part is that we need just lithography, or in this case, for our case, the flex that use currently, and it's very easy the the use of this stuff. We have two ways. The first way is heating the the polymer, or using what's the name for this, a gun, uh, for this for the polymer, and then the burn the polymer in mold in, in the in the two cases. One advantage of this is that if you have a heat polymer, uh, we can avoid the bubbles. That in this way we don't have the problem that we have with crystal tack. In this case, we don't use crystal tack. We can use it, but I think that we can use directly on the flex. Another advantage is the bond. How we can bond? At first, we hit the crystal plate, and then we put it on. Oh, sorry, we put it on the new device in the on the crystal plate with heat, and then with cold they bond uh, in, in stronger than the way that we use. And for and finally they use cool water to fix it on the plate. With this in this way, uh, we have a more resistant a device resistant to the high fluxes. Also, they have a via compatibility because this material is used in it's the material for that the the industry uses in the bags of the for all the petri dishes. Is super via compatibility. The flexibility is not that it it doesn't have the flexibility of the PDMS, but they have more resistance. I mean, when you have the PDMS and you try for that they used to broke, but in this case no. Here we have. the PDMS fracture point is lower than the EVA fracture point. Is another advantage. The terahertz transparency is it's okay because you can see the cell culture or wherever you want uh, inside of the device because they can PDMS is more crystalline than the PDMS. Mm, Here you have the absorption of the light in the PDMS is higher than the EVA. And I think that this is the critical point because the hydrophobicity in this device is better than the PDMS because with this we can avoid all the bubbles and the obstructions in the channels because with the with these this polymer have more hydrophobicity. All the all the liquids that can flow inside can throw easily that in PDMS. Mm, and here here we have the the contact angle in the PDMS is uh, um, is openly that the EVI contact angle, and they did experimental using USU mode, that is the photolithography, with a mixer device, and then they use um, this polymer is an electroactive polymer. That means that we can polarize all the device, not just one part. That's an advantage for if we have if we want to probe in in magnetic fields, for example, or electric fields. And another advantage for this polymer is that we can modify the device. Uh, what is the word? Okay, después de of the fabrication. With the PDMS, you have a device, and you can't modify it. In this case, we can modify it with heat, and that's all. It is very expensive, very low cost, is and easily because we have just 1 hour for obtain one a new device. With PDMS, we need to wait in the better case 2 hours or uh, one day. That's all. Questions?
Sorry, Daniel. Do you, search how much how expensive is this polymer? And I don't remember the other question, but that
Mhm.
was the first one.
It's as 60%, 40% over the PDMS.
Okay, it's not
But
so
but
expensive.
in pesos, I don't know.
In
Or
pesos, we don't work with pesos. We work with dollars. And I lost the question again. When you say that you can modify the chip, you um, you said that you can modify the surface, making another chemistry modification to, I don't know, ligand something, or you say that you can modify it with mechanical instruments.
Um, we can modify the architecture,
Okay.
the and the surface. Because if you have the complete device, you can hit this plate. Can you see my mouse?
Mm-hmm.
This plate you can hit this plate and introduce it in in the device because you can modify it with heat.
Ah, okay.
hmm
Okay.
that's the advantage. For example, if we forgot to do the inlet.
Mm.
Okay. And it's not a problem, the heat, or it has to be very high to modify this kind of chips?
I'm sorry.
If you can modify it using heat, it has to
hmm
be higher heat, high heat, because I don't know. One
hmm
problem is that the PDMs chips have dilatations or modification because the heat. In this kind of chips, the heat is a problem or not?
It's not a problem. This device or the the mold, the primal mold, for example,
Mm-hmm.
the flex or is U8 plate, they have an stop resistance of for the heat. I don't know what it is, but in this case, we need over of 100 degrees to modify it.
Very well. Thank you. I don't have any more questions.
I have a question,
Mhm.
Danny. Please, regarding the porosity, you can set me
Mm,
if it's the same that in PDMS or
The porosity, let me, I can remember reading about the porosity, but I can
because
check.
it's a biocompatible
It's biocompatible.
device.
Mhm.
Yes, but I think that this device require a wealthy una cámara húmeda.
Mhm. Um, I think that we can prove it. This paper is for the 2020, and I'm sure that we can search and obtain more information if they did another experiments with cells or something like that. But I think yes,
Mm.
because if you have if they prove this material in another assays, no in microfluidic, this is the first time that use it in microfluidic experiments. But I think yes, we can we can search about the EVA properties.
Okay, thank you, Danny.
You're welcome.
I have a question.
Ah,
Yes.
Danny, what about the bubbles? When you pour the polymer,
Mhm.
what happened with the bubbles in compare with the PDMS? We have to be very careful with the generation of the bubbles. What happened with this method?
In this method, I think that we have two ways to use it. The first one is we can replace the crystal tag in the first way because is easily, but I don't know if we have problems with the flex. That if we obtain this material, we need to prove with the flex, because if we have the same problems that the fusion, the flex with this material, we can use it. And but in another then the another way that I think is we can use in this way the first way they avoid the formation of bubbles if we compare it with the crystal tag, because we have problems with crystal tag with when we are made it the or make it the the device. If we replace it, they say that in this way we have less bubbles in all process of fabrication. But if your question is in the experiment, when you
No. When you make the device,
is in the two ways, in the both ways we have less bubbles.
so in order to avoid the vacuum step.
Mhm.
Okay, thank you.
Okay, Danny, one question. This material is it's a mix
Mhm.
of
Yeah, it's a mixture from methyl. No, where is that? And ethylene are the two materials.
which materials, or only the polymer and
And here we have ethylene and vinyl acetato.
okay. And in the figure 2, could you show? Yes. The mold is do you know which is the material of this mold?
No, just they say using pot. The mold. I'm sorry. Um, they report that they used um, a 3D printed mold because they prove with big channels over than 100 micrometers. That was the side they did.
Okay. Okay, thank you.
Thank you, Danny. Who wants to? Jose, you go or me, as you like. I can't hear you, Rocio. Sorry.
No,
Very low. Mm, Still low, but better.
¿Ahora me escuchan mejor?
Perfecto. En castellano era.
Perdón, ¿cómo?
Que en castellano se escucha mejor. Es un chiste.
Ok. Okay. So,
Do you want to start?
yeah, I'll do it.
Sorry.
Hi, everyone. I'm gonna be presenting this paper. It's a microfluidic chip for thrombogenesis by manipulation of the chip surface. So in this paper, the microfluidic chip fabrication and the surface engineer are employed to mimic the local pathological environment experienced in living arterioles. So to study platen activation and adhesion on different wettability surface, they propose a simple method for controlling micro-nano scale patterns and the chemical and topographic attributes on the silicon substrates. So merely by tuning a few laser operational parameters, the micropatterning surface can be simultaneously converted from hydrophobic to either super hydrophilic or super hydrophobic in just a short time. So to study the interaction of the microchannel surface and plated adhesion with different wettability pattern, geometries, roughness, and so the first thing they do is they dope the PDMS with hydrophilic silica nanoparticles, and then the surface in the microfluidic chip was micropatterned by a UV laser to produce these regions with different wettability. On the super hydrophilic surface, numerous micro-nano cauliflower-like structures are randomly, you see them here in part E, are distributed randomly in the rather smooth surface between the microcavities that are formed on a super hydrophobic surface. So the dope particles are here, you can see. They are suspending in the PDMS precursors, and then they will be precipitated over time before curing. So consequently, you have a thin layer of the particle concentration gradient, and that will be formed from nearly zero to the final average concentration near the surface. And they will be fixed after fully cured. So therefore, the authors hypothesized that hydrophilic nanosilica exposure after the UV laser ablation is the dominant factor for the wettability switching. So the ablation process decreases with an increase in the distance between the scanning lines of the laser. So the super hydrophilic surface has a maximum surface roughness, and the super hydrophobic surface has the maximum root mean square of the surface. The results shows that more micro nanostructures are formed on a super hydrophilic surface, while a profile high deviation are larger on the super hydrophobic surface. So then they deduced that the nanostructure of the topography was able to stimulate the plated adhesion as a biocatalytic function during the clothing process. So the topographies of the super hydrophobic and super hydrophilic surface were similar in terms of diameter of the microcavities, but the distance between the microcavity was really different, with 25 and 50 micrometers in the super hydrophilic and super hydrophobic surfaces respectively. And what's more, the area between the cavities are hierarchical structures on the super hydrophilic surface, unlike the smoother surface on the super hydrophobic. So these results suggest that cavities with a larger spacing between them act to increase the surface contact area for enhanced plated adherence by allowing this adhesion to occur. And according to other previous studies, the silica-water interface is negatively charged. So the platelets also have a negative charge on the surface in the presence of celiac acid. So they speculate that one of the reasons for the suppressing platelet activation with the few clots form is due to the platelets being repelled by the negatively charged superhydrophilic surface. It can be seen that the platelet-rich plasma droplets that they use here on part B have the maximum contact area with the superhydrophilic surface, obviously, while the contact area is minimum with the superhydrophobic surface. So few platelets adhere to the pristine PDMS silica composite surface. And by construct, a significant number of platelets adhere to the superhydrophobic domains. With the superhydrophilic domains, a much smaller platelets can be found. So the platelet coverage increases with the time in all of the three different wettability surfaces. However, the thrombus coverage of the superhydrophobic surface is the highest, indicating that this surface is highly thrombogenic. And usually, to reduce the blood volume and the time required for analysis, the surface of a microchannel is functionalized with bioactive proteins, which is a common platelet agonist. However, here in these experiments, they do everything without any agonist, and they observe significant platelet aggregation on the cyberhydrophobic surface of the microchannel in a very short time, around 2 to 3 minutes. So this microfluidic device has a potential to be used for a rapid platelet assays, while where less whole blood is required. And the dynamics of platelet aggregation on the cyberhydrophobic surfaces were investigated under both physiological and pathological conditions. And they saw that thrombus grow way faster and the coverage is much higher and the pathological conditions compared to the physiological ones. So in conclusion, these experiments clearly indicate that the microfluidic chip with the UV laser treated surfaces can act as a biosensor to monitor thrombus formation and platform to manipulate the surface thrombogenicity for a selection of biocompatible or high thrombogenic materials in tissue engineering. So that's all. Thank you. Any questions?
I think it's very interesting. I maybe lost this kind of chip can use to assign patients samples then, where it's going to be optimized person.
Yes, they can use drops of whole blood to do it.
Okay, drops. Very well. That it's maybe to find that they have any potential possibility to read the thrombogenicity in their blood, and then maybe look for the reason.
Yeah, for the reason.
Like a cream, yeah. Like a very.
Yeah, it's like a rapid assay just to have an image.
Yes, very well. Thank you. Do you have any questions? Well, thank you, Rocio. Very interesting.
You're welcome.
Well, then I go. Well, this paper was selected because it belongs to Acevedo groups. That is the same group that I am reading about their work since I started with you. I think that this work is pretty interesting because they are trying to use the microchips as a scale down model to accelerate the development of biopharmaceuticals chromatographies. They used a technology that I never read before, that is micromilling, that is used a drill. We have another paper only to show you the kind of system that they use. Let me show you. They perform in BMA chips the design using the drill. Oh, here. Very homemade, no? Well, they compare the results. First, they use the PMM to make a model. Then they use the one PMS, but PDMS, but is in another ratio, is 5:1, to make the negative model. And finally, they pour PDMS over this new model in the equation we use to obtain the chip. They compare these chips with 1 milliliter per pack column, that is the gold standard to work. That is the same system that I use. The first thing that was strange to me is the design of the chip, that is cuboid. They use it like a column. It's similar to the column geometry, but it's a cuboid, and the other is like cylindric. And they put here in this case, an anion exchange agarosa, and they used a frit. That is one of the problems to avoid to leak this agarose matrix to the outlet, and they use this frit that are spheres of PMM. And then, well, they used to sense the presence of protein on the system of interferometry. First, they designed the interferometry, that is escape what I want to tell you. Then they make this mold, and the system is very similar as we work. And then they compare the performance of the chip and the column. They use a console software to simulate the flow inside the devices. And then they find that they have differences in the performance. The 1 milliliter column have one front line peak, and when they use microchip systems, they find that the simulated one was before that they used they use solutions to find the front of the empty column and the packed column, and they have differences between the simulated one. And they try to explain why the microcolumn has a lower performance than the column, and they find several things that I think are interesting for us. One was that the packing of the density packing was lower, and they suppose that is for they don't have an frit in the inlet. Then when you put the arrows bits inside the column, the microchip column, you are going to insert them with high flow. When you stop to pack, that the bits can come back to the inlet, and they have another density than the one you supposed to have. The other thing was that PDMS is very flexible and make with the pressure and the packed column, make that the PDMS deform, have another form, and that also decrease the packing density. And that make the peak broader, and and they see a tailing in the peak, and they think that is that deformation is because the frit, the PMM bits that they use as frits, that making changes in the geometry. And and they have a bigger retention time, and that make the column less efficient. They think that they can change putting out that bits and using a lower height of that part of the channel to trap the agarose bit inside. Well, finally, they remark that these kind of chips are useful because they are smaller, they have transparency that lets to use microscopic-based analysis to characterize further, like to study the total and local porosity, to see the bit size and the fluid distribution inside the microcolumns. But that is a work in progress too. Well, thank you. Anyone have any question? Well, if you don't have any question, we can finish this meeting, I think. When the video is going to be in the drive, well, thank you. Bye-bye.
Thank you, Camille.
Bye, everyone.
Fer, ¿aló? ¿Me escuchas, Fer?
Sí, aquí estoy.
¿Qué tal? Oye, todavía no nos corten. Oye, quería preguntarte sobre el tema de los chips. Que si ya pudiste tener alguna idea referente a eso.
Sí, no van a entrar porque el stage que usamos en el microscopio tiene las medidas definidas, entonces si tiene un poquito más de centímetros no alcanza.
Oye, y
No
otra
sé
pregunta,
cómo.
me habían comentado que también estaban usando unos adaptadores tipo conectores Luer diré.
Pero para el chip.
Sí, claro, o sea, las entradas.
Sí, pero
Ya,
sí.
¿me puedes mandar fotos y las marcas y los modelos y eso? Porque queremos replicar acá esa idea, con eso para ver si mejoramos el tema de la generación de burbujas. De hecho, yo estoy acá probando con los que hay acá, pero parece que hay igual distintos modelos y quería ver cuáles son los que son ustedes.
Lo que tengo entendido es que tienen un diseño propio y lo imprimen en 3D.
A la puta madre.
Ajá.
Okay.
Pero
Okay,
con todo deja de ver
no...
si es que venden algunos otros o cómo tienen en eso.
No,
claro,
igualmente
porque digamos como...
si están hablando de los conectores que te va a mandar Elvesis.
Sí,
¿Te va a mandar?
Porque encajan bien en los lowers. Están hechos para encajar con los lowers. Yo los tengo acá, que son los que uso yo.
Claro, deberían tener, digamos, esa medida estándar, digamos, que
Sí, es una medida estándar que encaja bien con el lower.
Está bien. Sí.
Claro que es con los lures de los chips DVD, ¿verdad?
Claro.
Sí, sí. La idea era como que o fabricar el hembra para que esté encastrado en el chip, o sea, en la entrada, o colocar el macho, digamos. O ver si es que sale más barato comprarlos y nada, solo pegarlos, porque de hecho yo hice esa prueba y pegarlos funciona, pero el tema de como que fabricar o hacer algún símil de eso tiene ahí sus peros. O sea, yo logré hacer uno por ahí, pero no sé si es qué tan bueno sea. Y nada, de hecho quería saber si, digamos, quería conversar con eso con los jefes, aprovechando que ahora había esta pequeña reunión. Pero nada, acá voy a seguir.
Juan, yo tengo acá unos de los que tienen ahí ustedes. Ahora lo chequeo que encaje bien y te aviso. Así ya sabes que son esos, las medidas.
Dale, igual ahí te voy a mandar unas fotos con lo que yo hice.
Dale.
Dale, listo. Bueno, eso es todo. Chao.
Okay. Chao.
Chao.
Chao.